多少分？你多少分？啊，那你们算高分了吧？当时。对呀、但是老师也没说不能拿。那就行了，达到目的就行。不过咱那个没几个人，你business就没几个人，3分钟也说不了多少。
是。
可以没事。
3分钟说不了几个话。
稍微词儿准备，基本上没什么问题。
就是不在一个小的团队。
要知道他讲这个我就不来了，上一节课不该漏了，这节课我大概看了 PPT 也看了，没啥。
上节课也没弄呀，就ADF没什么弄呀。
ADF 还能听啊？是得听听。
但你都知道，上节课我觉得你都知道。听不听？
我现在有一些疑问，就是还没看。Cat 不是开始没报一鼻子，你知道吗？然后后来 Finance 是吧？满了啊。计算财务学是吧？是财务吗？Finance 吧？啊啊啊啊！为啥？present 不就 presentation 吗？这算啥？
而且这个好像不是 PPT，
就做 presentation 吧。
就是你写的东西，我不太清楚，没仔细看，我就看着我就觉得脑壳一炸。
哎，没事儿，出来个事儿。最坏的情况就是不及格，那又能怎么办？
没怎么办？
消耗。你现在改不了了啊！你现在已经过2周了，你怎么改？3分是吗？
是因为插错，不是因为没事，大哥说3方面我跟说了那么多次，我已经心里上了。
老刘弟，你今天又得验这一码。
只有2种可能，来，不，只有2种可能，就是迟到那么多和不来。
Okay, so last lecture I tried to explain some things about the way in which web architecture interacts with client web architecture. how we expect those to behave when we're dealing with information resources, things that we can retrieve over the network, versus non-information resources, things that we can't. What I want to look at today is start off by looking at this ontology word that I've mentioned a few times, this notion of some sort of formal vocabulary that we use. Now, last week I talked about RDF as a standard knowledge representation language that we use on the web, on using semantic web. And I've talked about the idea that a knowledge representation language like RDF is something that is application domain neutral. We can use it for anything, but we need to customize it to a particular application domain or domains in which we're interested. So this notion of knowledge representation is something that's absolutely central to the semantic web. It's, when we talk about knowledge representation, we're talking about really this field of AI that's looked at how we structure, how we organize data in such a way that we give it some meaning that lets us do things like reason over that data, that lets us query it in a quantitative fashion. If you look at what happens within the AI community, within the knowledge representation community, I should say, there is this sense whereby we talk about a good knowledge representation being something that naturally represents a given domain. And a poor knowledge representation as being something which is sort of unintelligible. We can't actually understand how it's representing the domain. Now, within the AI community, there's been a long-standing thread. This goes back to the 60s. And there are a number of different approaches historically that people have used. They've used formal logic, things like first-order predicate logic, or things built on top of that. They've used things like production rules, which typically are things that you express in the form, if this, then that. If this thing is true, then that thing must also be true. There's a chunk of work on things like semantic networks, and I've mentioned those briefly in the introductory lecture. So this goes from sort of Quillian's work looking at the speed of retrieval from memory. There's work from people like Marvin Minsky, who's brought up things like frames, which have sort of influences on everything from KR in good old-fashioned artificial intelligence to things like object-oriented programming. Now, when we look at what happens within the semantic web, the approaches taken on the semantic web pretty much combine all of these schemes, or rather, there are equivalences between bits of these that mean that they mesh quite nicely together. And I'll try and bring that out further on in the course. Now, the first part of this lecture is going to be a broad introduction to the notion of an ontology. The second part will be looking at a specific ontology language, RDF schema. Tomorrow, I want to start looking at description logic. So effectively, a particularly specialized type of formal logic that OWL is based on. Next week, I've still not quite agreed with Stefan and I who's going to do what. I think I'm going to have to do rather more lectures next week than I expected. So for the time being, it's fairly safe to assume that I'll be doing the lectures next week on OWL as well. So that's some sort of context for this. When we talk about traditional AI systems that are symbolic AI that use some sort of knowledge representation, these systems typically are taken to consist of two parts. A part that stores the knowledge within our system. So we talk about this as a knowledge base, not just as a database. So this is a place where we store the structured, organized data about our application domain, structured according to what particular approach we're taking. And then separately, we'll have the sort of the procedural part. So some sort of inference mechanism that we can use to examine the knowledge base, manipulate it, and answer questions, solve problems, or make decisions. Possibly do things like work out what things logically follow from the things that we already know. So this is a sort of standard separation, is something that we will also see within the semantic web. So the knowledge-based piece of the semantic web is the bit that will typically store the triples. Later on I'll talk about things like triple stores, specialized databases for storing RDF data. The inference part, the reasoner, is something that will work over those triples and let us infer new things that we didn't already know. So within this, you will see things like Sparkle Query Engine, the query engine to let us interrogate these knowledge bases, but also we will see reasoners that understand the semantics of ontology languages like RDS Schema and OWL, that is, that can understand the particular descriptions we've given of a particular domain, such that they can then infer new knowledge from that. Now, the way that these are built is they're built as general purpose mechanisms. We don't build an inference mechanism for a particular domain. We build a general purpose mechanism, and then we give it a suitably expressive description of a domain that lets us then infer new facts. These suitably expressive descriptions, in general terms, within the semantic web, are referred to as ontologies. Now, the bit where I look at the web scientists in the front row. Ontology is one of these words. If you talk to a philosopher about ontology, they will, if you talk to them about an ontology, they will roll their eyes and know you for a computer scientist. As far as philosophers are concerned, ontology, not an ontology, but ontology is a particular branch of philosophy. It's the branch of philosophy that's concerned with the nature or essence of being or existence. In other words, it's that part of philosophy that's concerned about what things exist. In computer science, we take a slightly different view of this. So this is quite a venerable description now. It's Tom Gruber's description that dates back to '93. So a brief sort of bit of conceptualization here. This chap, Tom Gruber, was involved in a big US defense project called the DARPA Knowledge Sharing Effort, DARPA being the Defense Advanced Research Projects Agency, the people that funded the early internet. The knowledge sharing effort within DARPA was an attempt to build a bunch of interoperable tools and languages to let different expert systems, so different knowledge-based systems, talk with each other. So within the knowledge sharing effort, there were a bunch of different languages they created. There was a thing called KISS, the Knowledge Interchange Format, which was a form of knowledge representation language. The experiences that they had with this led to a follow-up project called, in fact I'm trying to remember what the project was called. There was a further project that came out of, further language that came out of DARPA called the DARPA Agent Markup Language, or DAML, which was created by a chap called Jim Hendler originally. This is the same Jim Hendler whose name is on the semantic web paper. DAML is a knowledge representation language based on originally based on a description logic, and a version of DAML called DAML plus OIL was used as the foundation on which OWL was built. So effectively, this W3C language OWL is a version of a language that was derived from this language. So this notion of ontologies predates the semantic web quite happily. And the notion of ontology in this sense predates it quite a bit. We can trace this back over 20 years. Gruber's definition is, it's a very computer science definition. What is an ontology? It's the specification of a conceptualization. I say computer science because it's very specific and ultimately unhelpful unless you know what is exactly meant by the words. So, by a conceptualization, what he means is a description of the object, the concept, the properties, the relations, the entities that are assumed to exist in some application domain. In terms of a specification, he means a formal description. So this is a formal description of the things that exist in some application domain. Within the philosophical literature, you'll find this thing referred to as formal ontology, and there's a fair amount that's been talked about this in the philosophical literature as opposed to the literature. So I just note this down. If you're looking for philosophical papers on formal ontology, ontology. Now, within computer science, our view is that an ontology is an engineered artifact. It's something that we create, and it contains a particular vocabulary, so a set of terms that we want to use to describe the things, well, that we want to use to identify the things that exist in a domain. So the names of the different types of objects, the names of the properties that relate them together, and a set of explicit assumptions that describe the intended meaning of that vocabulary. So for example, our vocabulary might include, let's say we were coming up with a vocabulary to talk about an organisation and the people that work for it. So our vocabulary might include terms like company, person, employee, works for, and so on. The assumptions would talk about the relationships between those terms. An employee is a kind of person. An employee works for a company. So we have this distinction between the terms that we're introducing and how we describe those terms, how we define what those terms mean in terms of each other. Why do we care about this stuff? Well, the early work that was done on ontologies like this in the DARPA knowledge sharing effort was really about trying to build interlinguers, languages that let different communities, different pieces of software talk together. So it's all about creating a shared understanding between pieces of software or between communities. This expert system understands this domain and uses one set of terms, this one uses another set of terms. We define an ontology that they can use to translate facts from this expert system into facts used by that expert system. So it's about enabling communication. There are some fairly good examples of where this is used for establishing a terminology for a community of interest. So one of the examples of ontologies that I think I might have mentioned in passing was a thing called gene ontology. So this was a genomics ontology that was invented about 15 years ago by the genomics community, predominantly in the States, for describing genes, gene products, and the biological processes that certain gene products are involved in. Prior to that, there wasn't a common terminology for talking about different genes. It might be what we call a normative model. This is a particular vocabulary that we use to describe this application domain, and if you want to work with us within this domain, you must speak this language. This is how you must conceptualize the world. Finally, it's about interoperability, so sharing data between systems, possibly sharing data between systems over time. This gives us a way to, say for example, produce data that is proof against any sort of legacy problem, so that we've got some way of understanding what our old data can be used for. So when we look at the structure of an ontology, the two parts of it are really going to be the sort of names for things, which may include some sort of definitions, and constraints that exist on the concepts that have been identified by those names. So for example, an elephant is a kind of, an elephant is a concept whose members are a kind of animal. Elephants are kinds of mammals. A definition of what's meant by a herbivore. But then we might place particular constraints. So for example, all elephants are either African elephants or Indian elephants. Now, this is very much the sort of computer science view of what an ontology is. The one thing I'd note at this point is that there is a sort of countervailing view that says that an ontology is just a particular type of knowledge organisation system. It's a way of codifying some sort of qualitative knowledge. And we've got a long history of building those sorts of things. So informally, we can also talk about a bunch of other types of things as ontologies. So for example, controlled vocabulary, taxonomies, thesauri. This goes back to some of the things I said in the very beginning when I talked about the interactions between different disciplines that led to the creation of the semantic web. We have the hypertext people, we have the AI and knowledge representation people, but we have this other community, the library and information science community. And all of these types of knowledge organisation systems are things that pretty much originated within that community. So library and information science do knowledge representation, but they don't talk about knowledge representation. So they talk about things like cataloguing and classification and metadata. But at the heart of those things still involve, by the computer science definition, things that are ontologies. So to sort of walk you through some examples, a a controlled vocabulary. Let's look at some examples of, to consider some examples of these from the library world. There are things like the Library of Congress subject headings. So let's say, for example, you want to find a book on a particular topic in the library here. Now, you might know the title of the book, which is reasonable, but let's assume that you don't know the title of a particular book. You just want to find all of the books that are around a particular topic. Now, the way the library's been organised, there is going to be a shelf. We organise shelves, books by topic. We shelf them by topic. So, on a particular shelf, identified by a shelf mark, you'll have a bunch of books on a particular topic. How do you find that shelf? You might already know the name, so you might know computer science is going to be somewhere in QA76, but you don't know exactly where. So what you can go to is something which lists a bunch of keywords and then says where you can find those keywords within the library. That set of keywords, that explicitly enumerated list of terms, constitutes a controlled vocabulary. These are all the terms that are used to describe things within this library. And each of those terms will have a definition associated with it. Now, the thing is that these terms are not organised in any way. They're just keywords. So you go to the catalogue and search for a particular keyword, it tells you what corresponds to that keyword. It's just a flat list. There's no hierarchical structure. Now, we could put some hierarchical structure in there. So, for example, we could build some sort of taxonomy, and there are loads of examples of this. Broadly speaking, these hierarchical taxonomies will involve every term within one or more parent-child relations. So if we look at something like a library, we could be looking at, say for example, the relationship between computer science as a topic or a subject area and programming languages as a subject area. There is a sense in which one of these things, computer science, is the parent that subsumes the smaller topic within it. Now, there might be other types of parent-child relationship, and when we start talking later on about ontology design patterns, we'll look at some of these things as well. So we might talk about the difference between a type and an instance of a type. This is the notion of a person. These people are instances of a person. We might look at, well, genus species is sort of the more specific example I've given you, but we might specifically be looking at things like genus species distinctions within biological classification. We might be looking at part-whole distinctions. So, for example, Southampton is an authority area within England. England is a region that makes up part of the United Kingdom. So in that case, we have a part-whole relationship between those things. Southampton isn't a kind of England. It's not an instance of an England. It's not a specialisation of an England. It's a part of an England. So places where we might find these sorts of things, library classification schemes, most of the ones that are in use, Library of Congress as we use here, Dewey Decimal, UDC, all of these are hierarchical. So for example, if you look at something like Dewey Decimal, the 800s, if it starts with an 8, it's somewhere in the sciences. If you look at 850, I think that's maths off the top of my head. And if you look, things under 850 will be more specialisations within that area. So 850 might be physics, thinking about it. As I said, we could be looking at biological classification, so things like Linnaean classification, where we break things down from kingdom through phylum, class, all the way down to species and subspecies. Within things like the medical subject headings, which I mentioned on the previous slide, there are tree structures within that, and mesh is typically used for doing things like anatomical descriptions. So, your hand is part of your upper limb, your finger is part of your hand, and so on. Now, in fact, I did have some examples. Sorry, the 500s are the sciences and maths. So 500s is that, 530s is physics, 537 is electricity. Library of Congress, if you tried searching for stuff in the library here, it's kind of weird and kind of different. If it starts with Q, it's science, QA, calculus, maths, and you find computer science in there as a subset of, it's effectively a subset of the range for dealing with calculating machines within maths, for historical reasons. So we can have taxonomies like this, and the point with all these taxonomies is they're sort of single-rooted taxonomies. We can have taxonomies that have multiple hierarchies at the same time. Something like UDC, Universal Decimal Classification. Just think, did I mention that? For those of you who did web architecture last semester, I mentioned the guy that created UDC. So Paul Ottley had a hand in the creation of UDC. So the idea here is you can describe not just a single topic, but you can describe a relationship between topics. So for example, you might have artificial intelligence in 004 and clinical medicine in 616, but you could also talk about the intersection of those two things. So 004.8 colon 616 is the application of artificial intelligence to clinical medicine. And there are other things, so there are sort of tags on these things that you can use to indicate the language of origin, the language in which pieces are written. So you put 20 on the end and this thing's in English. Okay, we've got taxonomies that just give us, this is a specialization, so this is a generalization, this is a specialization. The next type of knowledge organization system from here is the notion of thesaurus. What these really give us, in addition to this sort of broader term and narrower term, is the notion of some other relation, a related term. So there are these two concepts. Neither of them subsume the other, but they're related in some sense. So an example of this might look a bit like this. So this is an example from a thesaurus that talks about a variety of things, including plants. So this is the entry for an apple. So the scope note, the description, the fruit of any member of the species Malus punilla. So apples have a broader term. They're a type of foodstuff. There are narrow terms. A Granny Smith is a type of apple, it's a subclass of an apple. There are related terms. So apples are related to cooking ingredients and taxable foodstuffs and horticulture. They're not sort of specializations of those things, but these things are related. We might also have, for apples, see also apple trees. Again, it's a related thing. It's not a specialization, it's not a generalization, it's something else. We might also include within this pieces of disambiguation. This notion of an apple is not the same as an Apple computer. Now, when we look at, through this lens, what we consider by an ontology, all of these things are starting to have bits that we can build up into an ontology. We have a set of terms, we have a vocabulary, we have some information about how these terms are related to each other, either in some kind of hierarchy or using these sort of broader related to relations. So within an ontology, what you typically find will be not just this thing is related to that, but an explanation of the types of relationship that exist between concepts. This thing is related to that thing by this particular concept. So what you'll typically find in an ontology will be a set of class definitions. So these are classes of object which we will find in this domain of interest, and those may be arranged into a hierarchy. So an employee is a kind of person, a person is a kind of entity, it's a kind of agent, and so on. We'll also have a bunch of definitions of relations that can connect instances of these classes together, and those might be related to each other in terms of hierarchy. So for example, we might talk about an employee works for a company, and a person is affiliated with an organisation, and works for is in some sense a specialisation of being affiliated with. It's a special case of that. Other things we may find in ontologies, constraints on how these things are used. We may find axiomatic knowledge, these things are always true. There may be sort of rule-based knowledge, which brings us back to our procedural representations. So the sort of summary of this piece, if we build all these things up together, if we start off with a controlled vocabulary and had a hierarchy, we've got a taxonomy. We take a taxonomy and add some sort of lateral related to relations, we have a thesaurus. If we take a thesaurus and add type relations and constraints and rules and axioms, that we might properly consider to be an ontology. But the point here is that there is this spectrum of different types of knowledge organisation systems. from something that might be very sophisticated and contain lots of very sophisticated kinds of knowledge to something that is basically just a predefined bag of words with no further meaning. And we could arguably talk about all of those things, we could arguably use all of those things when we're using the semantic web. Okay, right, that's the first half of this. Any quick questions on what I've just talked about before I go on and start talking about RDF schema? Okay, right, so what I was trying to talk about there was ontologies in very general terms, the sorts of things you'll find in an ontology, how they get related to each other, and so on. If you think back to the semantic web layer cake, we have RDF as the knowledge representation language, and on top of that we have RDF schema. RDF schema is a language for defining vocabularies for use with RDF. Now, slightly confusingly, it's defined in RDF schema. So RDF schema is used to define itself. It is an RDF vocabulary that's used to define other RDF vocabularies. Effectively, what it contains within it are classes that we can use to define classes and properties that we can use for defining the characteristics of classes and properties. So how classes and properties are related to each other, what their ranges and domains are. There's some other sort of ancillary stuff in there as well. So, for example, places where you can say, you know, for this class, see also over there, for this thing, its definition is over there, and so on. So, let's try and walk through some examples. The point with RDF schema is there's very little actually in it. So RDF schema first lets us define classes. So to define a class in RDF schema, you say that a particular thing is of type RDFS class. This thing is of type class. And you can then happily go on after this and start saying, well, okay, I've then got things that are of type person, for example. So here I've given this in RDF XML notation. We could have instead written something like, hash person is of RDF type RDFS class, if we were to do this in N3. So to declare something as a class or to define a class is a single triple. Now we can say other things about classes. We can say that one class is related to another class. So we've got a definition of person. Let's say we want to talk about the class of employees as a specialization of person. So here we have something with a couple of triples. So employee is a type class, and also employee is a subclass of person. So what we're effectively saying is this class of object is in some sense a subset of that class of object. Even just with this little bit, there's a bunch of stuff that we can do already in terms of inferences that we can make, that we're permitted to make by the semantics of RDF schema. So the first thing that's worth pointing out, this property, RDF subclass of, is transitive. So let's say I've got a little piece of the class structure here. I've defined three classes, a part-time employee, which is a subclass of employee, and an employee, which is a subclass of person. From this, I can infer that actually a part-time employee must also be a subclass of person. So this is what we mean by transitivity. You can effectively join subclass relations together and draw new ones as shortcuts. The next thing we can talk about is the reflexivity of subclass. Now this is a little bit odd, but it's kind of required to make the semantics work properly. What this basically means is if we have a class, any class, every class, that class must be a subclass of itself. So if we have a class called person that was declared to be a type RDFS class, it must automatically be a subclass of itself. And this is like saying every set is a subset of itself. Okay, so these are the first two bits we can say. We can talk about transitivity and reflexivity. We can also talk about distributivity. So here, we've got a little class hierarchy, an employee is a subclass of a person. I've got a particular person here who is an employee. Now, when we say employee is a subclass of person, we could also read this as saying all employees are persons. So if we know that John Smith is an instance of employee, is a type employee, he must also be an instance of type person. So this property, we say this property, IDF type, distributes over the subclass property. Also, I note at this point that these things all combine together. So for example, if I had, say, 3 classes, A, B and C, and I said that these things were subclasses of each other, and here I've got a particular object, let's call this X, and I've said that X is of type C. By this rule, I can say that, well, this thing must also be of type B. However, because subclass is transitive, I can also say that C is a subclass of A, and because I can combine that with this, I also know that X must be an instance of type A as well. So each of these little separate rules can be combined together. Right, so that's all you need to know about defining classes within RDF schema. RDF schema is a very, very simple language. Very practical, it's good for most of the applications you'll need. I'll go a bit further, but RDF schema is very simple, very to the point. But this is only part of it, because we've not talked about properties yet. So in RDF, we can define a property that we can use as the predicate of a triple. We can do this by saying that thing is of type RDF property. There is a slight fiddle here. You'll notice it's RDFS class, but RDF property for historical reasons more than anything else. It's more of a little legacy bit that we've got stuck with. So just as down here, I've written hash person of RDF type RDFS class. Here I could write EX works for the sort of RDF type RDF property instead of this sort of rather more long-winded RDF XML. Now, a couple of lectures ago, I had somebody ask a question about object-oriented programming. Who was that? Right, okay, this is the slide for you, okay? Because you may look at this, so quite a few of you probably will have done some OO programming in something like Java or C++ or C#, and you'll be looking at this and thinking this will look very object-oriented. It is, but there is a key distinction between the way that RDF defines things and the way that things are defined in an object-oriented language. So if you look at an OO programming language, you define classes in terms of the properties that they have. So you define a class person, and you say that this thing has got a bunch of attributes. It's got a name, it's got an age, it's got an email address, and so on. The way that we define things in RDF, rather than defining classes in terms of the properties they have, we define properties in terms of the classes that they relate to, the classes whose instances they relate to each other. So we won't say a person has a name, a person has an age, a person has an email address. Rather, we would say there is a property has email address that runs from class person, instances of class person, to instances of class email address. So effectively, if I have, let's say, let's draw out that example I've just given. Here's class person, and I've got something that's an RDF type person. Let's say this is John. Let's say over here I've got a company. Let's say this is what I know Acme Incorporated. So this thing is an instance of that company. I want to talk about how this property, about this particular property that relates people to companies. So this might be something like works for. And what I'll do is define this by saying this property, wherever we see it, always goes from things that are type persons to things that are of type company. We call these two ends the domain and the range. So the domain is the end that the property runs from, the range is the end that the property runs to. If you want to think of a mnemonic, if you're firing a cannon, the range is the distance that the cannonball goes to. Yeah.
So in terms of triples, is the property the predicate?
So the property that you've got here is what you would use as the predicate of the triple. So actually that's a really good point, because there is a very subtle distinction that gets made when this stuff gets written about formally between the middle bit of the triple, which is the predicate, and what fills in that middle bit of the triple, which is a property. So a predicate is the component of the triple, but the thing that fits into the predicate place is a property. So we could define, in fact just as I've drawn on the board, we could define a property like works for. So here is the thing, it is a type property. This thing goes from things that are of type employee to things that are of type company. So we can define properties like this in terms of the classes that they relate to each other. We can also define hierarchies of properties. I've already said a little bit about this. So we might have the notion of a property affiliated to, between a person and an organisation, and then a specialisation of that, works for, which might connect, I don't know, an employee and a company. So just as we have a hierarchy from subclass to classes, we also have a hierarchy based on subproperty of the properties. Now, there are quite a few extra things that we can infer using RDF schema once we have properties in there. We're not just limited to making statements about the types of objects. So the first thing is that the subproperty of is something that is transitive and reflexive. So just as it was for subclass, so every property is a subproperty of itself. If I have property A that's a subproperty of B, and property B is a subproperty of C, then property A is a subproperty of C. What I can also do is entail superproperties. So let's say that I know that John Smith works for Example Incorporated. And I also know that works for is a subproperty of affiliated to. That means that I can then infer that if John Smith works for Example Incorporated, he must also be affiliated to Example Incorporated. This is what we mean by specialisation or a generalisation of the property. Other things we can do, if we know things like the ranges and domains of properties, we can infer types, we can infer class membership. So let's say I have my property here, works for, relating John and Example Incorporated, but I know things about this property. So for example, I know that this property has a domain, that's employee, and I know that it has a range, which is a company. Because I know those two things, and I know this triple, I can also infer that because John is being used as the subject of a triple whose predicate is worked for, John must also be a type, an instance of employee. Similarly, Example Incorporated must also be an instance of company. Now that is basically the entire semantics of RDF schema in a nutshell. What have we got? Something is a class, something is a property, a class is a subclass of another class, a property is a subclass of another property, a class is the domain of a property, a class is the range of a property. That is the core modelling bit of RDF schema. One hand and one thumb. So there's very little that you really need to think about in terms of RDF schema. There's very little vocabulary to worry about. Now, RDF schema does include a bunch of other stuff, and I mention this in passing it's not something that typically you'd need to worry about. So within RDF schema, there are a bunch of classes that get predefined. So, you know, the notion, the class of classes, the class of properties, as I say, it's got a different namespace for very obvious reasons. The class of resources, basically any type of object. The class of literal values, the class of data types, so you can talk about integers or floats or dates or what have you. The class of XML literals, and I can honestly say for that one, I have never ever seen that appear, but it is in the spec. These predefined classes within RDF schema have some sort of hierarchy. So for example, you know, what is a class? Well, a class is a kind of, it's a subclass of resource. A data type is a subclass of class. What else do we have in here? All of these things here, explicitly string, explicitly integer, are all instances of data types, but also subclasses of literal. So one of the things that actually makes RDF schema a little bit awkward to deal with if you're building a reasoner is there's a lot of sort of self-referentiality in here. In practice, for anything you'll be doing, you probably won't need to worry about this. If you end up doing research in this area, you probably will, because there are some very subtle gotchas in here. But for the purposes of this class, I'm including this just to say, actually, you don't really need to be worried about this stuff, because practically you won't need to. So that's almost all of RDF schema. The only other bits are these ancillary features, the other little bits on the side. And these are actually really common. You'll see some of these very frequently. So there's a property called RDFS label that we can use on anything to give it a human readable name. Because remember, these URIs that we're using to refer to things could be very long and very awkward. There are times when, for display reasons, we just want to give people a nice human readable label that they can understand. So RDFS label is typically used for that, whether for classes or properties or other types of things. We also have a property called RDFS comment, which is used to give a human readable description of something. Now we'll talk more about this when I start talking about the process of building an ontology, in particular how you document an ontology. But this is typically used to give things like human readable definitions. So when you're building an ontology, if you define the class of employee, so this is a description about employee, which is a type RDFS class, and it has a property on it, RDFS comment, which gives what it is. An employee is a person who works. And the point here is that this is intended to be human readable. It's not for consumption by a reasoner. Other little bits, C also is defined by, which are they're used frequently. They have no formal meaning. None of these ancillary features have any formal meaning as far as a reasoner is concerned. But what you often use these things for is to point at something that's related, but we're not being very specific about how it's related to something. So you'll often find these used for as part of the documentation for things in your ontology. So this class of objects, actually the definition of this class is given by that document over there, for example. Right, final bit. So if we look at the path by which RDF has been built, RDF schema has been built, it goes back quite a long way. So when I first started playing around with semantic web stuff in 1998-ish, 97, 98, RDF schema already existed at that point. The problem was the early version of RDF schema was really not very well specified, and it never made it to a standard. It was a sort of a draft standard, a proposed recommendation, but it never sort of made the hurdle. In fact, it never even got a proposed recommendation. It never made the hurdle to actually become a proper recommendation. When that early version of RDF was revised and published in 2004, there was a revision of RDF schema. So the first standard version of RDF schema is about 13 years old. There's a slightly more recent version of it that came along in 2014 that basically tidied up some of the way the document was written and nailed down some of the semantics a bit better than it had been previously. I don't think there's any real significant difference in how RDF schema, what RDF schema is used for or what it means. It's just the standard has been clarified. So some of the slightly ambiguous places have been removed. RDF schema. If you look on the website, just get a if you look on the module website, down in the list of things you can do, in amongst the worksheets there is a worksheet for doing things with Sparkle that basically walks you through the steps to build a simple semantic web vocabulary using RDF schema. This is actually really worth having a look at, because one of the things that this walks you through, I mean there are some nice diagrams in for a start, but one of the things it walks you through is how you might go about building a simple ontology. So for example here something talking about academics and students and universities and modules, but how you go about building that by extending another existing ontology. So in this case the ontology that's been extended is FOAF, this friend or friend ontology that's used for social networks, but within it contains notions of persons as a type of agent, organisations as a type of group, and the relationship between groups and agents. So this lets us talk about people being members of an organisation, for example, and it basically walks you through how you would go about building that. So how you would go about defining the classes, defining the hierarchies between those classes, so student is subclass person, academic subclass person, how you go about documenting them, so putting some comments in there to explain what they mean, how you would add properties to these things, how you would talk about the sub-property relations between things, and how you would define them, how you define their ranges and domains. So it's worth having a read through this. You should be able to sort of cut and paste some of the ontology definitions out of here and stick them into the RDF validator that W3C provides, which will give you nice visualizations of what's happening with each step. So I strongly recommend that you have a go at this. If you haven't already kind of worked through the RDF worksheet, please have a go at that as well. Okay, any questions? Okay, well thank you very much. Have a good evening, and I shall see you tomorrow.